understanding force. Okay, force is the easiest way to look at force, and this is what's going to happen a lot. In fact, y'all are going to probably take a whole entire class based on this whole concept of springs. So specifically what we're talking about is to kind of just imagine this. Okay, imagine you have this little tiny little spring and you put a weight on it. So as that weight's just sitting there nice and happy, it's actually it has a force applied to it. Okay, and then as you start pulling on that spring, then all of a sudden the force is increasing. The force that's you're adding to the whole system is increasing and increasing. And you notice how how most springs work, that as you pull on them, it gets harder and harder and harder to pull, because when you start stretching it out, it's harder for you. It's almost like a weight, and it's harder to pull apart. Well, that's a force that's keeping everything together. It's acting against what you're trying to do. It wants to stay in that nice little equilibrium state. When you start pulling on it, then that's what's force is what's kind of fighting you. It's what's fighting you back, because it wants to go right back to its normal form. Okay, so let's talk about some concepts here in force. F, obviously the variable F stands for force, and it's measured in newtons, which is an N. Then we have K as being the spring rate, and what that spring rate means is more of what's fighting against you. It's when you start pulling it out of its happy state, that's the spring break. It's how it's changing, okay? And it's measured in newtons per meter. Displacement is how far apart you're pulling it. Okay, so do I pull it a meter? Do I pull it 2 meters? It's how far apart you're pulling the mass that's sitting on it from starting to finishing. Okay, and then of course F naught is just the initial force, and that's measured in newtons. Okay, and if we look at this little graph for 2 seconds, it kind of shows you how this all is really a linear equation. You have your initial force value, F naught, it's your y-intercept, okay? And as I start pulling it, that mass along a direction, and so like 1 meter, 2 meters, 3 meters, you can say it's all changing by a linear constant, okay? And the slope of this equation is K. So this is definitely more of the equation that we want to know, and as you notice, it's linear. I can write it as y equals mx plus b, okay, where how far apart the displacement right here doesn't really matter. It's an independent variable. Whether you pull it 1 or 2, it's up to you. It's your choice. It's just independent. And then the force, which is your y, that's dependent upon how far you're pulling apart. If you're just going to pull 1 meter, this much force is applied. If you pull 2 meters, then it's a much greater force. So depending on how much force is in the system, it's always dependent on how far apart you're pulling the object from its happy state to its non-happy state. Alright, let's go to our example using these topics. And again, it's going to be something very similar to what we did in the last two. Okay, we want to find the spring rate K and the preload constant, or the preload force F naught, and the following values of force and displacement are known. Okay, and again, if you kind of look into these charts, it's saying that when I have pulled it 0.1 meters, the force is 1 newton. When I have pulled it 0.9 meters, the force is 5 newtons. So this is more of your X column, this is more of the independent variable, and this is your Y column, because force depends on how far apart the displacement, what's the meter there. Okay? And if we start this equation just how we kind of been doing the other ones, we have our general y equals mx plus b, or in this case, instead of y equals mx plus b, we have force is equal to our spring constant times our displacement plus our initial force. Okay? And if I want to find our slope, which is in this case our k, that's going to be difference in our displacements. Our differences in our forces. I've got to put my y values on top. So 1 minus 5 over the difference in our displacements. So 0.1 minus 0.9. And when I plug all this into a calculator, what comes out is 5. So our k value is 5. And like before, if we want to kind of go ahead and start our equation, then that means F is equal to 5y plus our initial force. Okay. And if we want to find our initial force, we'll just choose one of our values. I'll just say 0.1 and 1. Let's plug it into our equation. So 1 is equal to 5 times 0.1 plus F naught. And solving this out to finish this up, we'll get our initial force to be 0.5. I guess let's go back in. Forces in terms of newtons. So there's one part of our answer. And then our spring constant is in terms of newtons per meter. Because in that fraction over here on the left, newtons are on top, meters on the bottom. So we can say K is 5 newtons per meter. Okay, that was one of the other things they wanted us. And if we put this all together in one grand equation, we'll say force is equal to 5y plus 5. And there's our big equation. And real quick, making sure I put that as 0.5 as that last part. Okay, let's move on to the next one. Example 2. We're going back to electric circuits. And just want to let you guys know this is actually kind of out of order. If you wouldn't mind just kind of scrolling down just to the next page right here. That just got out of order for just a second. But we want to talk about quadratic equations first before we really we did 3 examples on the linear equation, and we're about to do 3 examples on the quadratic equation. So you know the linear equation, y equals mx plus b. Let's focus real quick on the quadratic equation. Okay, do y'all remember the basic quadratic equation? Quadratic equation in general form, you know, it's just y equals ax squared plus bx plus c, where c basically represents our y-intercept, or like before, it's our initial value. Let's see, x are our independent variables, y is the dependent, just basically like linear equations. And then how in order to get the x-intercepts, the methods that we can do to find the x-intercepts are either to factor, we can use the quadratic formula, or we can complete the square. And those are all the different 3 methods on how to find the x-intercept specifically. Because c is going to be your y-intercept, so how to get the x-intercepts when you go 0 is equal to ax squared plus bx plus c, then these are the 3 methods that we can use. Okay, so let's go back up really to example 1 right here. Let's talk about this for 2 seconds. Okay. In example 1, a projectile is being fired in a vertical plane. Okay. And the reason why we want to consider this more quadratic and less linear is when you think about it, when you shoot a cannonball or you throw a tennis ball or throw a football, does it fly in a linear pattern or does it fly in a parabola, which is a quadratic pattern? And I'm thinking most times we're flying in a quadratic pattern, so that's why it's in this section right here. And as you can look at it, that the height of this object is dependent upon time. So how long this object is being flown in the air will tell you what the height is. The height is going to go up and then it's going to come down. Okay, and the reason why it's quadratic, and we definitely have it quadratic with a t squared there, just to show that it is going to be following an arced pattern. So in this first part, we have our basic equation here, just h of t is equal to 96t minus 16t squared. We want to find the time when the height is 80 feet. Then we're going to plot this and then find the maximum height. Also find the time t when the height is 144 feet and the time it takes to hit the ground. So we've got several things going on here. Okay, so let me write our equation down here just a little bit lower so when I change screens, I don't have to keep coming back all the time. Okay, and the first thing they want us to do is find the time. So how long does that object have to be in the air for us to be at 80 feet? Okay. So part 1, we want to find t when our y value is 80. So coming over here, 80 is equal to 96t minus 16t squared. So at this point, here's a quadratic equation. You're asked to solve a quadratic equation. So for all we want to do is always before is just, I'm going to move these over so we have it set equal to 0. I'm going to move it over to the left so that way my t-squared term, my leading coefficient is positive. Minus 96t and then plus 80 equals 0. Okay? And from there, if we first divide through everything through by 16, just so we can reduce this, our equation becomes much simpler. It becomes t squared minus 6t plus 5 equals 0. So if we factor that, it'll factor to t and t. Looks like a minus 1 and a minus 5. So at t equals 1 and at t equals 5, then our height is going to be 80 feet. Well, does that kind of make sense? That you're actually going to hit 80 feet twice? Well, of course, because once going up and then once coming down. So if this is kind of 80 feet right here, then what we can say is right here is 1 second and right here it's 5 seconds. So somewhere between 1 and 5, we're going to get the answer to our next question. But the next part says we want to find the maximum height. Well, obviously that top of that curve has got to be somewhere between 1 and 5. So let's go about finding that. Oh, here, let me box this up before we call this done. So at 1 second and 5 seconds, the height is 80 feet. Okay, so let's go about finding the height right there. Well, if you remember from quadratic equations that in order to find the vertex of a quadratic, you use that formula negative b over 2 times a, and then what you do is plug that back into your function to get the y value. That's what that all says. Okay, so in our equation we have, if we write it back up here again, our height is 96t minus 16t squared. Okay, well that is a and this is b. So our x value, or in this case is our t value, because our x-axis represents time, is going to be negative b, so negative 96 over 2 times a, so 2 times negative 16. Okay. And we plug that into our calculator real quick. We will get a t value of 3, or in this case 3 seconds. Okay, so at 3 seconds, so between 1 and 5, it's kind of right here at 3, we're going to hit our maximum height. And what is that maximum height? Well, let's find h of 3. So 96 times 3 minus 16 times 3 squared. And that will give us a maximum height of 144 feet. Okay, so we can say that if we want to write this as the max height is 144 feet at 3 seconds. Alright, box that up, and that answers another one of our questions. So moving right along throughout this.